Warning: the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a video for college algebra students or students in pre-calculus as well, on how to solve large systems of equations using a method called Gauss-Jordan elimination. This generally is initially called Gaussian elimination, but there's a slight modification to it by a mathematician with the last name of Jordan. There you go. And that creates the Gauss-Jordan elimination method. So we're going to walk through how the method is kind of built, and then after that we'll actually do an example, and then in a separate video I have a series of examples. Just as a heads up, where we're going with this is to have an augmented matrix. If you've already done this type of stuff and you're very familiar with it, then you obviously do not need this video. However, generally using a matrix, specifically an augmented matrix, to help you solve a system produces a method that is very algorithmic in form, so you don't have to kind of guess your way through it. Instead, it's a very step 1, step 2, step 3 style of method for solving a large system. So let's start with the basic question. If both sides of an equation are multiplied by a non-zero constant, will the solution of the resulting equation change? Well, you could see this with just a simple example. This is not a proof, but an example. But if I told you I had x is equal to 2, you would say the solution therefore must be, well, x equals 2. If I were to multiply both sides of that equation by, let's say, 3, then the question is, will this resulting equation have the same solution? And the answer is yes. You would divide both sides by 3 and you'd get right back to the solution. So, just based on an example, not a proof, but an example, if both sides of an equation are multiplied by a non-zero constant, the solution will not change. This, by the way, holds for larger equations. For example, let's suppose that we had the equation x plus y is equal to 2. Now we know one solution of that is 1 comma 1. Now let's go ahead and multiply both sides of this equation by, let's say, 10. 10x plus 10y is equal to 20. Does 1 comma 1 solve this equation as well? And the answer to that is definitely yes. So still in this situation, it looks as though if a solution works for one equation, it should work for the other equation where you've multiplied by a non-zero constant. So again, this is not a proof, but it showcases the general idea. By the way, this is the birthplace of the elimination method, and that's why the elimination method works, is because for when I say elimination method, I mean for solving systems of equations. And this just is part of that method because when you're solving a system by elimination, sometimes you multiply both sides of an equation by a non-zero constant. The second question, if two equations having the same solutions are added, what will be the resulting equation's solution? That's a weird wording there, for me at least. Well, let's take those two examples we created. Let's take a look at this first one. So you have two equations, they have the same solution. If you add those two equations up, let's go ahead and I'll use blue and add those up. The resulting equation that you will get is 4x is equal to 8, which, by the way, has the same solution as the two equations above, x equals 2. So that seems to imply that if two equations with the same solutions are added up, then the summation of those two equations still has the same solution. But let's just check out over here. Again, remember this one had the solution 1, 1. If you add those two equations up, just adding them up like this, you get 11x plus 11y is equal to 22. Remember we said 1, 1 was a solution. There's an infinite number of solutions to these equations. However, 1, 1 was just one of them. Well, notice 1, 1 will solve that equation as well. If you think that that's just a little trick because with the solution 1, 1, you could try any other solution that would have worked for that first equation, like 2, 0. Well, 2, 0 works here as well. If you let x equal 2, you get 20. Y equals 0, you get 0. Well, 20 plus 0 is 20. And if you let x equal 2 here and y equals 0 there, again, you get down to the same solution, which is 20. Or you get down to the same identity, which is that 22 is equal to 22. So no matter what, it looks as though if you add up two equations having the same solutions, the result will still have the same solution. And I've written that in right there. Now we can use these facts to create an algorithm to solve a system of any size. But before we do, we need a structure that'll help us track the number of operations. So there's a huge amount of operations that can get involved when you use these methods. And as such, you want to make sure you minimize your chances for making mistakes. Also, just to let you know, when you involve these structures, it starts to begin an algorithm. So remember, when you solve a system of equations by elimination, you have to decide what variable you're going to eliminate. And as you grow your equations to 3 by 3, your systems to 3 by 3 systems, or 4 by 4 systems, and so on and so forth, that decision-making process gets in the way. It actually becomes a little bit of a bulky decision-making process. You spend more time trying to figure out the right way to go rather than just tackling the problem. And so building in these structures helps out significantly. We'll start with this idea of a matrix. If you have not dealt with matrices before, matrices being the plural of the word matrix, then you're in for a pleasant journey through matrices. Right now, we're just going to do a very beginning introductory journey through matrices. They're very easy. It's just a rectangular collection of data consisting of m rows and n columns. For example, this guy right here is just a collection of data, and because it contains 1, 2, 3 rows and 1, 2, 3, 4, 5 columns, I'll write that down as well, we would call this a 3 by 5 matrix. And generally speaking, we just do it down here. So we use these brackets to denote that we're talking about a matrix. And then, of course, you have a row of data, another row of data. It's just like an Excel spreadsheet or a Google Sheets data sheet. And then we just call that a 3 by 5 matrix. The general notation for matrices, not that we are going to use them here, but just to let you know, we use capital letters traditionally for matrices. And if you want to indicate the size, you can say capital A and then a subscript 3 by 5, indicating the matrix has 3 rows and 5 columns. Again, with what we are going to be doing, there is no real need for us to use this notation, the capital A notation, because when you're first learning to deal with matrices, you're not really, especially with systems of equations, you're not really doing matrix arithmetic. You're just using a matrix as a placeholder for information. But giving you a heads up right now, there's a whole field of study on the arithmetic and on the advanced arithmetic of matrices, and that's called linear algebra. But that's not the purview of this video, nor of a college algebra course. The second structure that I want to introduce, which is based on that first structure, is called the augmented matrix. You only really talk about augmented matrices when you are given a system of equations. So this allows us to transpose or rewrite a system of equations into a matrix. We just need to delineate the difference between the terms that have variables actually, and the terms that don't have variables. So this is a very bulky definition. I'll read it out loud in a moment, but I'm just letting you know it's better to see an augmented matrix than to read the definition. So here's the definition that I wrote. The augmented matrix of a system of m equations consisting of n unknowns, where each equation has all variable terms on one side and all non-variable terms on the other, is an m by n plus 1 matrix, where the final column consists of the relevant non-variable terms for each equation. And just to let you know, we traditionally put a vertical pipe separating the coefficients of the variables and the constants. I'll showcase this with a simple example right now. So here's a system, and in this system we have 3 equations. Let me write that down off to the side. We have 3 equations, and in this case, if you look through each equation, you could see that we have x, y, and z, so we have 3 unknowns. Now, these equations are not written in a way that works well with a matrix right now, and according to the definition, we are told that all variable terms should be on one side, and all constants or non-variable terms should be on the other for each equation in this system. So if you look at that very first equation, unfortunately there's a variable term on one side that should be moved to the other side. So what you start to do initially is just to move all terms with variables. I tend to move them to the left-hand side and then leave all non-variable terms on the right-hand side. So I'm going to subtract 3x from both sides here. Notice how I'm stacking them in columns. This is the x column, and this will be my y column. And finally, I'll have a z column here once I'm done moving things around. You can see in the second equation that on the right-hand side, we have a non-variable term, the 9, and a term with a variable, the negative 4z. So I want to move that 4z to the other side. I'll add 4z to both sides, and I'll stack it in the column with the z's. And then the final row in this system, I have a constant, unfortunately, on the side that's supposed to only contain variable terms. So this constant is on the wrong side, and that variable term is on the wrong side. So I'm going to subtract z from both sides and subtract 11 from both sides. So subtracting z from both sides and subtracting 11 from both sides, that's what I get. So this is the initial setup. Notice, again, I have a column with all my terms involving x, a column with all my terms involving y, a column with all my terms involving z, and then finally a column on this right-hand side, which is a column of constants. And that's the general initial setup, just cleaning things up like that. Also, it's super helpful if you get rid of fractions initially. So if there were fractions in here, let's say this is a -3/7 or something like that, you would multiply that row by 7. And we already know from our previous discussion that if you multiply a row of an equation or a system, or maybe I should just say, if you multiply an equation by a non-zero constant, its solution will not change. So multiplying both sides of that top equation by 7, for example, would not change the solution. So we'd still be working with the same system of equations in essence. Now, we are going to write the coefficients in a matrix. So I'll just write a matrix bracket there. I have a -3. I'm going to go by columns here. So -3, 6, and -12. And then the next column will be 2, -1, 2. That's the column of y coefficients. And then -1, 4, and -1. That's a column of coefficients of z. And then we have the column of coefficients, of constants. -2, 9, and -11. This would be a matrix containing the coefficients of the variables and then a column for the constants. This would be called an augmented matrix because it represents the system of equations, and we generally put a vertical pipe right here. You don't have to. I've seen a lot of books that don't, but I prefer it personally for me, just because it lets me know where the equal signs go in my equation. That's all. So to the right of that vertical pipe would be all the constants. To the left of that vertical pipe would be all the coefficients of the variables. That's kind of a nice way to keep it. Also note, we had 3 equations and 3 unknowns, yet this is not a 3 by 3 matrix. It's a 3 by 4 matrix. And that is because we added an extra column for the constants on the right hand side. And that augmented column grows the number of columns by 1. So normally with 3 rows and 3 columns, you have a 3 by 3 matrix, but with our column of constants, that adds just 1 more to this system, or to this matrix. So this is the augmented matrix for that system of equations. Pretty easy to set up, actually. Just a little bit of cleanup to the initial system, and then write the coefficients in and separate the left-hand side and the right-hand side with a vertical pipe. Now, the ultimate goal when working with an augmented matrix is to get it into this form right here. You want to eventually be able to manipulate it to get into this form. Remember, this column right here stood for x values. This column stood for the y values, the coefficients that is, and that column stood for the coefficients of the z values. And so if you were able to somehow, using some algorithm, get your augmented matrix to eventually become something like this, you could then rewrite this and say, well, okay, this tells me that I have 1x plus 0y plus 0z must equal that constant. Or in other words, x is equal to c sub 1. And the second row of that tells us that 0x plus 1y plus 0z is equal to that second constant. And that would imply that y is equal to c sub 2. And obviously this would also mean that 0x plus 0y plus 1z is equal to c sub 3, or in other words, z is equal to c sub 3. So if we can get our augmented matrix into this form by manipulation, we would have the answers to our system, right? We would find out what x, y, and z are. So the big question is, how do you do that? The answer to that question is that you use the 3-row operations. Scalar multiplication, so let me write down what that is. That's just multiplying a row by a non-zero constant. Remember, the rows of an augmented matrix just represent equations. And if you multiply an equation by a non-zero constant, its solution doesn't change. So we are perfectly allowed to multiply an equation, and therefore a row in an augmented matrix, by a non-zero constant. So scalar multiplication, perfectly allowable. Row swaps. Well, row swaps, I don't even need to write anything about that. The reality is, if we're working with, let me hop back a couple pages here. If we're working with this system of equations right here, it doesn't really matter if I had written this equation as equation number 1 or this equation as equation number 1. In other words, I could swap the positions of these equations and the solution to the system would still remain the same. In fact, I could take that very top equation, wrangle it up here, let me grab that guy, wrap it up, and move it all the way to the bottom, and guess what? The solution to the system is still the same solution as before. So that is the basic idea of row swapping, is that you're allowed to swap rows within the augmented matrix as well. Now you might wonder why you would ever do that, and we might see examples of that as we move forward, because that can be very useful. It's probably one of the least common moves when solving using the Gaussian elimination algorithm, but it is still very useful at times. And then finally, adding non-zero multiples of one row to another. And I call this the kill step. The kill step, you would take a scalar multiple of one row and add it to another row, and that is used to eliminate a variable. Now, you will understand this when we actually do an example, which is our next step. So we might as well just go ahead and see how this works. And while it is possible to describe this method step by step, Gaussian elimination and Gauss-Jordan elimination, it's actually better to see the method through an example because it's so robust. And I tried to write out a step-by-step method, but it ended up being very convoluted, so it's just easier for me to start this way and just say, okay, well, we'll just keep it like this. So an important thing to remember, though, is to carefully keep track of your operations, and this will help you find mistakes in your work. And I'll showcase how I carefully keep track of my operations using notations. Okay, so let's demonstrate Gauss-Jordan elimination on this system that we had written down earlier. Now, just to let you know, when you start the Gauss-Jordan elimination or Gaussian elimination, whichever you prefer, and I'll tell you the difference between the two when that difference is necessary, you're going to need a large piece of paper because you're going to do a lot of rewriting when you go through this. So the first thing you do is you create the augmented matrix, which I did by just taking the coefficients of the equations. So I took all the coefficients of x, put them in the first column, and so on and so forth. And then I have that augmentation bar, and that separates the coefficients of the variables from the constants. All right. Now, remember, I only have 3 things I can do. It's a game, really. Our ultimate goal, let me write it at the very bottom right here. Our ultimate goal is to arrive at that picture, that augmented matrix. That's what I want to do. And I can only use 3 rules to do this. The rules of the game are as follows. You could swap rows if you want to. You can multiply a row by a non-zero constant. And you can add multiples of one row to another row, which is called the kill step. The important thing to remember is that you're working off the main diagonal, this diagonal right here. That's the main thing to remember here. You're constantly making decisions based upon that main column. The way that I do Gaussian elimination and Gauss-Jordan elimination, which are essentially the same thing up to a certain point, is that I work from the main diagonal downward, and then once I'm done working from the main diagonal downward and I arrive here, and I'll just let you know, actually maybe I should just showcase that. So again, I start with my eyes on that main diagonal, and then I will use this element to kill everything below. Then I move to the next main diagonal element and use that to kill everything below. And then I use the next diagonal element, and if there's more equations below, I'd use it to kill everything below. But once I'm done kind of killing things below, I then have arrived here, and I start using that to kill everything above. Then I hop back over to this next diagonal element and use it to kill everything above. And at that point, hopefully, we will have arrived at the end game, which is that augmented matrix down below to the right. So let's showcase all of these moves. I'm going to erase my messiness here, and then we'll start. So the very first thing, a lot of people, when they are learning this method, they're told to force this first coefficient to be a 1 because that's what you want it to be in the end. But actually, it's probably a bad idea in some cases. Some cases actually be fine, but I will only force that to be a 1 if when doing so does not create fractions. So for example, what's a way that you can get -3 to turn into 1, and your only options are swapping rows, which there's no other ones here, so there's no way to force that to be a 1 by swapping or trading rows. Or you can multiply this equation by a non-zero constant, and that's really the idea. I would multiply this equation by a -1/3. If I multiplied by a -1/3, I would get a 1 there. So just imagine that we did that, -1/3, and I multiplied everything in this row by a -1/3. The problem with that is that I would get fractions everywhere, except for the first element. The first element would become a number 1, but then the second element would become a negative 2/3, and the third element would become a positive 1/3, and the final element would become a positive 2/3. I don't like that idea. So in an effort to avoid fractions as long as possible, I will not bother making that a 1 yet. You can always hold off on that until the very end. If there is a way, by the way, to, let's say, force that to be a 1 without getting fractions, so in other words, divide by 6 that entire row. If you divide that entire row by 6 and you don't get fractions, then do it and swap rows 2 and 1. But again, in this case, if I divide that middle row by 6, I will get fractions. So same thing, the bottom row, if you divide it by a negative 12, you'll get fractions everywhere. So because of that, I know that there's no way to really start this problem with forcing a 1 in that initial coefficient there. So instead, my advice is to look through the rows and find the smallest coefficient. That's just a good idea. Now, I'm not saying that's a good idea for a computer to do that, because generally there's some issues with that decision when you're working with a computer, but when you're doing this by hand, I definitely would recommend find the smallest of these coefficients, and if that smallest coefficient was in a different row, swap rows. So again, my advice is, if it can be done without creating fractions in the augmented matrix, force the first main diagonal element, that would be this guy, to be 1 by multiplying the top row by its reciprocal. If you can't do that, which is very common, because you'll end up getting fractions. So if you don't want to do that, then basically swap rows so that the smallest of the coefficients in this first column is at the top. And I wrote that advice down below. And again, it is not, these are just pieces of advice, rules of thumb. You do not actually have to follow this word for word because there are lots of different tactics to approaching this. But I am just giving this as advice because I think it's good advice. So in this case, there's really not much we can do. Dividing any of those rows by the reciprocal of the lead elements in those rows would create fractions. So bad news throughout, and the smallest number is already at the top, so we're good. Once you get that done, you enter what I call the kill step. The kill step means that you're going to use this main diagonal element right here to kill off everything below. I'll go ahead and write that down here. Let me zoom in. So I call that the kill step. Use the main diagonal element to kill all elements below. So let me showcase how I would say that up here, because this is where I note to the world what I'm doing. And the way that's done is the following. You want to take twice this row, and in fact, let me give myself a little more room here. You want to take twice row 1. You want to add that to row 2. That will become the new row 2. Notice my notation there. This is a very common notation. I just put it right next to the row that I'm going to be killing off. I'm going to be killing off that 6 right there is what I want to do. So right next to that, I say, well, how am I going to do that? I'll take 2 times this row. So 2 times a -3 would give me a -6. And if you add that to that +6, you will totally kill off that +6. It'll become a 0. At the same time, I'm going to note that I want to kill off this -12 as well. And again, the entire time, you're really just using that diagonal element right there to do it. So that highlighted element is used to kill off the 6 below and the -12 down below that. So what would you multiply -3 by? So that is the opposite of -12, so that becomes a +12. Well, you would multiply it by -4. So I'll take a -4 times row 1, so that would be a -3 times a -4, or 12, and you would add that to row 3, that -12, to become the new row 3. Now, generally speaking, I don't showcase any of my mathematics when I do this, but because I'm assuming that you've never seen this before, I'm going to go ahead and showcase my mathematics down below. Actually, I'll showcase it down below. So I'll take twice row 1. I'm doing this in red to match this red notation up here. I'm going to take twice row 1. So 2 twice row 1 is the following. -6, 4, -2, and it's augmented with twice -2 is -4. Okay. And I'm going to add that to row 2. Row 2 is 6, -1, 4, and it's augmented with 9. In the end, when you add those up, you'll get 0, 3, 2, augmented with 5. So that's my new row 2. That is the new row 2 right there. Okay. And then row 3, I'm going to take -4 row 1 and add it to row 3 to become the new row 3. So let me write that down here. I'm going to go ahead and say -4 row 1. Well, -4 times row 1 is 12. -4 times 2 is -8. -4 times -1 is +4. And we have an augmented with -4 times -2 is 8. Now, in this process, and like I mentioned up above, an important thing to remember is to carefully keep track of your operations, because what's going to happen is you'll make arithmetic mistakes. That is going to happen. It's not that I'm saying you can make arithmetic mistakes. I'm saying you will. That's just how Gaussian elimination sometimes works, is that you run into or you make silly little mistakes. So you want to be somewhat meticulous with your work so that you can find your mistakes if you ever make them. So right now I'm rewriting row 3, which was -12 to -1 and -11. In the end, you're going to add those up and it'll give you a new row 3. So let's see, we have 0, -6, 3, and 8 minus 11 is -3. All right. So now I'm going to go ahead and write my new matrix. So our old matrix was that one right up there. And in fact, I'm going to go ahead and swoop that up and copy it. And that makes my life a little bit easier if I do that. So copy. And let's go ahead and scroll down and I'll paste and I'll move it. Okay, there we go. And let's zoom in here. And I'm going to erase all this stuff, and I can keep that highlighted there. Well, no, I don't. I don't care to, so I'm going to erase that. It's supposed to be a negative. All right, so let's go ahead and remove this row 2 and this row 3 because we've written a new row 2 and row 3. The new row 2 right up there is 0, 3, 2, and 5. The new row 3 is 0, -6, 3, and -3. Notice we're getting close to this structure right here. Getting close to it because we now have almost like a 1, 0, 0 in that first column. Well, it's not exactly a 1, 0, 0. It's a -3, 0, 0, but it's close. Then I pretend as though I'm just starting the problem again, and I say, well, all right, I would like to, and I don't focus on this anymore. I actually almost in a way say, well, ignore for the time being. Let me do it this way. Let's see if I can do this. I'm going to ignore this row and I'm going to ignore that column. And I'm just going to work with the remaining stuff here and pretend as though I'm starting a brand new problem. So again, I'm not looking at the top row and the first column because I'm done working with those for the time being. And I just focus in on these. I know those top rows and columns are there, but I just don't want to look at them for the time being. Okay. Now you don't have to obviously blot those out, but I'm doing that for our benefit for simplicity. All right. So now if I'm starting the problem all over and I have this matrix, I just say to myself, well, if I divide this row by 3, that'll give me fractions. So I don't want to do that. If I divide this row by a -6, that would give me fractions. I don't want to do that. So make sure that between these two rows, the smallest value is in the main diagonal. And remember, the main diagonal is this guy right here. That's my main diagonal. And notice the smallest element is definitely in the top of that main diagonal. That's exactly what I want there. It's not necessarily that you have to put the smallest element there, but it's nice to do that. Okay, so I'll leave that as is. And now I need to ask myself, how am I going to use this main diagonal element to kill everything below? So again, I quickly just enter into the kill step. And when I enter into this kill step, I'm going to use that main diagonal element right there to kill everything below. When I say everything below, I mean in its column. So in this step, I'm going to take a -2 times row 2, because this is technically row 2 still. I'll take negative twice row 2, and I will add it to row 3 to become the new row 3. Let's see what that looks like. A -2 row 2 is going to give me -6, -4, and -10. And row 3, well, that's just -6. Whoops. I don't want the -2. I want a +2. Oof. You'll see that, by the way, when you do your mathematics. So sorry about that. Take 2 times row 2 there. So if you were pulling your hair out saying, wait, that doesn't make sense, you're right, it didn't. So sorry about that. 2, and this will be 10. That does happen every once in a while. Then row 3 is -6, 3, and -3. You know you've done something wrong if you go to add these up and that first row does not be, or that first column, sorry, does not add up to 0. So that was my issue when I started doing that. I realized when I was going to add them up, it wouldn't have become a 0. So I would have been doing something wrong. So adding these two up becomes a new row 3. My new row 3 is 0, 7, and a nice little 7. So let's go ahead and rewrite our matrix. I'm going to just copy it here. Again, just like I did before, I just do a lot of copying in this work. So copy, and then I'll paste it down below if I have room, which I don't. So I'll paste it up above. I'll just paste it right in this screen right here if it pastes nicely. Yes, it does. And I should, just for your benefit, I should put in a vertical pipe here to let you know that this is separate from that work. There we go. All right. So, but my new row 3 is not that. My new row 3 is actually, let's zoom down here, 077. So 077. Now, actually take a look at this and compare it to where we want to end up. We're getting very close. And in fact, in this case, now, again, just like before, I'm going to say, okay, now that we've dealt with this top row, and now that we've dealt with this second row, we've therefore dealt with the top column, or the first column and the second column. We only have that little bit to work with, and I could easily divide that by 7 to force that to be a 1. So that's what I'm going to do here. I'm going to divide row 3 by 7 to become the new row 3. So I'm going to write that off to the left here. 1/7. Oops, I want to write it in red though. And I also want to give myself some room to write. So let me scoot this over. There we go. I'm going to take 1/7 times row 3, and that'll become my new row 3. This is just me multiplying a row by any non-zero number I want. And so this is a good use of that. And so when you do this, you essentially just rewrite your entire augmented matrix. Just grab that matrix. I'm going to copy it, and then I'm going to scroll down a little bit and paste it and rewrite that new row 3. Again, all I'm doing here is multiplying this entire row by 1/7. This becomes a 1 and a 1. 0 times 1/7 is 0. 0 times 1/7 is 0. So those don't change. That's the beauty of this method, is that it starts speeding up as you move forward. Now that we get to this point, what we're going to do is, so this at this point is actually called the Gaussian elimination. So this would be finished. Gaussian elimination is basically working from the main diagonal, this piece right here. Sorry, I'm just trying to get it. You're working with the main diagonal and killing everything below using the main diagonal. That's Gaussian elimination. And then what Gauss did at this point is he put it back into equation form and used back substitution. What Jordan did was a little extra work, which was he then, he arrived at this one, having used the main diagonal to kill everything below, he then kept with the main diagonal and started killing everything above. But instead of starting at the top element and killing everything above, he instead started with the bottom diagonal element and killed everything above, and then worked his way backwards. So again, the visual for the Gauss-Jordan method from this point forward is this. Use this one to kill everything above, then move to the next diagonal element and use that to kill everything above, and then you'll be done. Okay, so that's what we're going to do here. So again, I've just noted that we are now ending Gaussian elimination and starting into Gauss-Jordan elimination, which is using the diagonal elements to kill everything above. And we're starting that kill step right now. We're going to take and that's what's also nice about having this element be a 1. It's super easy to do. We're going to take negative twice row 3 and add it to row 2 to become the new row 2. If you do that, you get a negative 2 times 1 plus 2, and that will give us a 0 there. We're also going to take just regular old row 3 and add it to row 1 to become the new row 1. That's what we want to do there. So let's go ahead and write that down. I'll take negative twice row 3, which is 0, 0, 2, 2, and we're going to add it to row 2. And row 2 is 0, 3, 2. Oops, I said negative twice, didn't I? Negative 2, thank you. Notice how I always catch myself right there when I see that something's not going to cancel. It's a really good step. Anyway, let's see, add it to row 2. So row 2 is 2 and a 5. There we go. And you're going to add these up. You get 0, 3, 0, 3. That's our new row 2. At the same time, we'll go ahead and take row 3 and add it to row 1 to become the new row 1. So row 3 plus row 1 becomes the new row 1. All right, let's see what this looks like. Row 3 is 0, 0, 1, 1. And row 1 is negative 3, 2, negative 1, and negative 2. You're going to add those up, and the new row 1 is negative 3, 2, 0, and negative 1. Let's go ahead and rebuild our system. This time I'm just going to draw it out because the system is so significantly different now. So our new row 1 is negative 3, 2, 0, negative 1. There's an augmentation bar right there. The new row 2 is 0, 3, 0, 3, and then the row 3 is still the row 3. Notice that we're getting closer to where we want to end. Also, now you get to, so I've used this element to kill everything above, so we're done there. Now you go to the next main diagonal element. Now in this main diagonal element, you can immediately force it to be a 1 by taking that entire row and dividing by 3. So that's what I'm going to do right now. Because remember, keep your eye on this prize down here. We want to get a diagonal of 1s and 0s everywhere else on the left-hand side, and then just constants on the right. So love it if I could force this main element right here, main diagonal element, to be a 1. And I'll do that by multiplying by 1/3. So 1/3 times row 2 will become the new row 2. Now, you can see I use a lot of space with this. So what I'm going to do is, again, draw in a vertical pipe here so that I can just continue my work up above. So I get a -3, 2, 0, -1. -3, 2, 0, and a -1. The second row is what I'm multiplying by 1/3, so that'll be 0, 1, 0, 1. 0, 1, 0, 1, and the final row was 0, 0, 1, 1. And we are almost done, actually. I know it seems long-winded. It is when you're initially showing people this method, but actually, once you start using it, you get faster and faster. Next thing you know, it takes you only like a minute or two to do this. It's really not terrible. But now I'm going to use this main diagonal element right here to kill everything above. So this is, again, my kill step. So kill step to kill things up above. I'm going to go ahead and take -2 times row 2. Let me rope this up and move it so I can write this next to it. Move that over. I'm going to take -2 times row 2, add it to this row 1 here to become the new row 1. Now, instead of me writing step by step everything out, I'm just going to do it now. So you can do it this way. Row 3 doesn't change, because that we are not changing. Row 2 technically does not change either. What changes is row 1. And how does row 1 change? Well, we're going to take -2 row 2 and add it to row 1. -2 0 added to -3 is -3. -2 1, so -2, plus this 2 is going to be 0. -2 0 plus 0 is still 0. And then -2 times -1 is, -2 times 1 is -2, plus this -1 is a -3. And finally, you can see kind of the last step here, divide that full top row by -3. So I'm going to write it as -1/3 times row 1 becomes the new row 1. Barely fit that in there. But you get down to this. -1/3 times -3 is 1. Anything times 0 is 0. And -1/3 times the -3 is again 1. And we get the form we desired the entire time. This tells us that 1x plus 0y plus 0z is equal to 1. 0x plus 1y plus 0z is equal to 1. And 0x plus 0y plus 1z is equal to 1. Or in other words, x equals 1, y equals 1, z equals 1. That is the solution to this system. Again, when you look at this process, it looks terribly long. I totally get it. However, this is actually a much faster method than kind of guessing your way through the elimination method. It's a good algorithmic way to go through and solve a system of equations. And you'll see as we move forward in our examples in the next few videos that it will speed up.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.